Welcome to our notes for 7.2. This would have been day 2 if we were in class together. We would have worked today on what is called the washer method. You may have looked at the volume of a washer back in your geometry class. It is essentially a cylinder with a hole drilled into it. And this is not a perfect example, but I do have a model here. We'll get to sort of its entirety later, but you can see that here we have a 3D object, right? But right down the center, there we go, it has a hole inside of it that is itself a cylinder. And so we're going to talk about why this happens. How could you look at a graph and know that your 3D solid of revolution would be a washer version rather than a disk method? But first, we're going to review what a washer is. So go ahead and take a second and see if you can remember how to do this. And I'll walk through you here. If you wanted to take a minute and pause it, you can try it first. When you're talking about a washer, typically what you'll say is you'll talk about two radii. You've got an outer radius and an inner radius. And so I can think about the center of the washer as being both the center of the outer circle here and the center of that empty hole that would be in the center. And we would talk about calculating first the volume as if there was no hole there. So for example, I could say that the volume for the cylinder with that black radius would be pi. And then in this particular problem, my r is 8. So 8 squared and 0.1 is my height. And that gave me 6.4 times pi. And then if you recall from geometry again, you would next figure out the volume of the inner cylinder, essentially the volume that would correspond to your empty space. And I would go ahead and think of this as pi, right? The inner cylinder here, we've marked it with a radius of 4, and the height is exactly the same. So that gives me a total of 1.6 pi. But this represents the empty space that we don't want to include in that larger calculation. And so the overall volume, right, we can talk about the volume of the outer versus the volume of the inner cylinder. The total volume of our washer would be the outside minus the inside. In this case, 6.4 pi minus 1.6 pi for a grand total of 4.8 times pi. Oftentimes you'll see a specific formula written just like this because they both involve pi's, r squareds, and h's. The pi h would be factored out. Let's see. Get rid of this parentheses here. I would write pi times h, and then I would be left with r squared minus r squared, where the capital references your outside radius. That would essentially be the outer piece here. And the little r represents your inner radius. That's the radius for what you're going to subtract. So if I put that together, I would have in this problem pi times, my height is 0.3. And I could say that the outside radius is 3.5, the inside radius is 2, and I would get 2.475 times pi for my total volume. It's this formula right here that we want to take and modify. The difference with washer method is essentially that you have that hole in the center. So we're going to continue to call capital R the outside radius as if you did not have a hole drilled through the center. And we're going to continue to use little r to represent the empty space or the radius of that inner cylinder on the inside. So the overall formula, if you're going about the x-axis, is volume equals pi times the integral from a to b of capital R squared minus little r squared all times dx. Notice there's no square on the outside. It's just outer radius squared minus inner radius squared. This is where r and little r are both functions written in terms of x. So let's try some. Let's sketch out the first region. So we want to start with the region bounded by y equals x squared. I'll give you a hint. It works out to be in the first quadrant. So here's y equals x squared. And if you were to plot y equals x squared and x cubed are pretty close to each other. Let's think for just a moment what happens though, right? At 1, 1, they would have the same values. But if you took something like a half, right? At 1/2, y equals x squared would be at a quarter, but y equals x cubed would be at an eighth. So the cubic should be living below. And then after 1, it would actually rise more quickly. So it rises more slowly in the beginning and more quickly at the end. And you have sort of this banana shape right in between. And it says here we want to, in the directions, revolve around the x-axis. The thing is, the x-axis is not a boundary on our region. If we look back and compare to yesterday's notes, every time we did a rotation, the axis of rotation was actually a boundary of our region. I don't have that here. And the other thing to notice is that if you drew in one of these cylinders, your center is always going to come from the axis of rotation. And notice I'm falling through, or I'm going through open space before I even hit my region and get to the end. That's another cue. If you are sketching in one of those cylinders and you notice that you're going through this open air, then that is a signal that you are using the washer method. So now we've got to go through and determine our bounds and our capital R and our little r. So let's see, my boundaries, same as they were in the previous section. I want to think about where I would start drawing cylinders and where I would stop. This one is a horizontal axis of rotation, so this is a dx kind of question. I'm going to go from 0 to 1. And if I think about the outer radius, that is all the open air plus going through the region. So that would put me on the top curve. So that is y equals x squared. So my capital R is x squared, and I want to square that value, right? My capital R is x squared, and I square it because of the formula. And then I subtract, and I would want to think about my little r. So little r is what you're getting rid of, right? Little r corresponds to that open space, and that is being controlled by the height of your cubic function. So that would give me x cubed here and squared per the formula. And you can go ahead and put that into your graphing calculator. You could do it by hand if you had to. But we'll just use Grapher to make things move along a little faster. So from 0 to 1, you can type it in as x to the 4th, or if you're ever not sure, type it in sort of exactly how you wrote it. And let the calculator do the math for you. So that's a little tip so that you don't make unforced errors. So you can see that I have it typed in, and my solution comes out to be 0. Let's see, you could write 179 or 180 if you round it. Take a second, hit pause, and try the next one. I'll assume you've already done it, but let's walk through it anyway. We are interested in the secant function. We've got to draw that one in. We've got x equals -1 and y equals 1/2. Oh, I think I missed something. I just noticed in my key I did positive and -1. So let's draw a quick sketch here. X equals -1, x equals +1. And if you recall at 0, right, cosine of 0 is 1 over 1. It's going to give me a point right here. And secant is a U shape that's opening upwards. So it would look something like that. And y equals 1/2 would be a horizontal line right about here. Hardest part might have been remembering and recalling how to graph that cosecant function. But there's my region, and I would like to rotate it around the x-axis. Again, you do not need to sketch in the full three-dimensional solid. Just think about what it would look like to create a couple of radii. So it's good habit to maybe consider more than one, just in case something strange happens on one side versus the other. But I do think a quick sketch of the radius gives you a really nice idea of looking at and seeing how to set these up. This one is slightly more complicated. Let's see. I set mine up as volume equals, and then I actually used symmetry here because the left side and the right side are the same. So instead of putting 1 pi, I did 2 pi. But then I only integrated between 0 and 1 because the volume over here would just be mirrored the exact same volume on the left-hand side. So that's a little tricky. You didn't have to do that. You could have put a 1 pi and then a -1 and +1. That would have been fine. And I want to think about how I would draw the capital R. Recall, capital R is going to go through from the axis of rotation all the way to the outermost curve. And so it's that secant curve that is controlling the capital R value. Whoops, I drew the wrong radius right here. So it's that secant function that is controlling my capital R. So that would mean that I want to take secant x and square it. And then the inside function, right? What is it that I'm subtracting? How do I define that open space? Well, it's always the same value. If you look in this particular picture, right? It doesn't matter if I'm over here, it's a half a unit, or here it's a half. It is a constant function. It would be 1/2 quantity squared. So my capital R was the secant, my little r was the 1/2, and I have a dx. Go ahead and try typing it in your calculator. Secant is a little tricky to do. I've got 2 pi, math 9 from 0 to 1. And I cannot type in the square function as if I might want to. So let's take that and type in 1 over cosine x. And I want to square that quantity. So there's my secant quantity squared. And then half I can square in my head, that's a quarter. So minus 0.25, and I'll hit dx. Hopefully my calculator's in radians. Yep, that is the correct answer. So I got 8.215. Always, always radians for your units. I'm right in the middle of the glare spot there. So there you can see how I typed it in to match up. Turning the page, we're going to do the exact same thing, but rotating across a vertical axis of symmetry, or using DYs. This video will be a little long. You can always take a break. The formula is much the same, right? If I want to rotate around the y-axis or something parallel to, the capital R is still going to be through the open space and then through the corresponding region. Little r corresponds to just the radius for the open space. So my volume would be pi times the integral. We'll say from C to D. If you look in this picture, they've used C to represent the lower bound and D for the upper bound. And again, capital R squared minus lowercase r squared times, this time, dy. And also this time, R, and including C and D as well, are all going to be in terms of y. So capital R and little r are functions in terms of y. C and D would also need to be y values in order for this to be set up correctly. So let's try one. I don't think we need two here. So time savings, let's just hit this one. We have the exact same image, right? I have my same sort of banana shape. Here's y equal to x squared. Cubic would be just underneath it. And I'm interested in the region bounded right there. Except this time I'm going to rotate it in this direction. It's quite a bit bigger of an object. It would almost create like a bowl shape. And because it's traveling in a different direction, it's going to create a completely different solution. It does matter which direction you're rotating in. So for this one, let's again draw a picture right through the open space and through the region. That segment would be my capital R. So I have volume equals pi times the integral, right? My region was from the origin to 1, 1. So this time still 0, 1, but this time I'm pulling those y values when I'm writing that. The radius itself, right, would be dependent on that cubic function. Now I have to be mindful here. Y equals x cubed is equivalent to x equals y to the 1/3. I don't want to use the x cubed if I'm doing a dy kind of question. So my outer r is y to the 1/3 all squared minus the inner r, right, would be just this value from the open space's radius. So the open space is determined by the quadratic function. That is the leftmost curve that I'm running into. And that would be, right, if y equals x squared, then x is the square root of y. So y to the 1/2 quantity squared. This represents my capital R. This represents my lowercase r. And then I went ahead and I put it into my calculator. You can enter it any way you like. You can use the properties and simplify as you go. You can type it in just like this. Let's see, number 9. Get out of the glare here. From 0 to 1. Let's see, I'm going to type in x to the 2/3. So x to the 2/3 minus, it's y. If I square the half, I'll just get to the first power. Thinking. And my solution was 0.314. So far, we've only revolved around the axis. If we move away from the axes, things are a little bit harder. But again, it's going to boil down to segment addition. The rules are the same. If you have a horizontal axis of rotation, like we did on the front page, you'll have a dx problem. If your axis of rotation is vertical, you know you have a dy question. So here's an example. Find the volume of the solid generated by rotating the region y equals x squared and y equals 4x. So y equals x squared must be this one down here, a little curvier. Y equals x squared. And my linear function, right, the straight line, y equals 4x. And I would like to rotate that around the line x equals -1. So they've already shaded the region for us, and we're going in this direction. Ask yourself this question before you set it up. Are you working with a dy or a dx? If you're not sure, right, always going to create your radii from the axis of rotation and then heading out towards. And so if you think about, I can't really draw the whole cylinder here, but I can think about that the dy in this case, right, the little tiny width of these cylinders is measured in that y direction. That's why the vertical line is creating a dy question. So that means everything I want to do needs to be converted to y's. So that would mean that x is equal to the square root of y. And for this one, x equals y over 4 would be important for me. Let's see, the other thing I know I'm going to need would be the point of intersection. Where does x squared equal 4x? It would be at 0, and then also, let's see, x squared minus 4x. It would be at 0 and 4. So the 0 is here. That would make this one at x equals 4. Y is equal to 16. All right, I think we're ready to set it up. We've got volume equals pi. I'm working in a dy, so that would mean that I want to use the y values to set up my bounds from 0 to 16. And my R squared. Let's see, capital R all the way through the center, or from the center to the edge. So all the way through the open space, I've drawn in a capital R. This one, let's think about it. If I want to go just this far, I know that that's 1 unit. And then if I wanted to consider all the open space plus all the way through the region, that means that I'm going from the axis to the quadratic. So that would be my square root y. Right? It should be larger than that. I'm adding 1 unit. So the capital R is 1 plus the square root of y. And the formula is to square capital R. And then I would subtract, right? And let's think about if I drew in a lowercase r, right? That is from the axis of rotation all the way through the open space. So again, with the 1 unit, and then this time it would be to the linear function y over 4. So that would be 1 plus y over 4 quantity squared. And that is my setup. If you throw this in your graphing calculator, you should be getting 201.062. If you didn't multiply the pi through, it's actually an exactly nice answer of 64 pi. I did one more, and it's very similar to this, but this time we're going to move our axis of rotation closer. So here, right, I had moved further away from the shape. So in the next one, we're going to move closer to the shape. And so it's going to be a little bit different in how I set up my R values. Last example. So we have graph the region bounded by x equals the square root of y plus 3, and our nice linear function, that would be nice and easy to graph. Let's pick a couple points here. If y is 0, then I would be getting x is 3. So that puts me right about here. If y is 1, then I would be getting a 4. And we'd have to go all the way up to 4 to get another good point. So at 4, I would be getting 2 plus 3 makes 5. So 5, 4 is on my graph. It is a half a parabola going like that. And the linear function, let's see, is going to be, let's try plugging in 3. At 3, I would be getting 0. At 4, I would be getting 2. Right, with my slope of 2, I'm going to hit here as well at 5, 4. So I don't have a ruler at home today, but there's my linear function. So hopefully you can see that the region that I'm interested in is right here. This time, we want to rotate our region, if I keep reading, about the line x equals 2. So that would move me closer than the axis was. Let's see. So this one's going to be set up a little bit different. However, if you draw a picture, if you sketch in one of these radii, you can really start to see what's happening. So let's just randomly pick a point on our axis. We'll think about, if I'm rotating about that line, this is a dy kind of question. I have a vertical axis. I'm cutting through all the open space and the shaded region. That is my capital R. So let's think carefully about what we know. We do know that this length is 2 units. We also know that the outer edge of that capital R is being controlled by the half a quadratic, right? The x equals square root y function. The thing is, when I plug in a y value, for example, when I plugged in 1, I moved over 4 relative to the y-axis. So when I am using the actual function, right, I'm actually measuring this whole piece from here to here, would be the x equal to square root of y plus 3. So this time I have the whole coming to me from the function, the part that I know is 2, and the big R that I'm trying to find would be the other smaller parts. So how can I write an expression for capital R? Well, it would be the whole, right, from axis to outer edge, minus the portion that I moved over, that smaller part. So that means that capital R here would be square root of y plus 1. Likewise, right, if I wanted to think about little r, what's happening? Well, that would just mean that I'm moving over until I hit the linear function. So in order to calculate little r, I would be taking the length or the value from the function. Oh, I've got to edit this, don't I? This would be what? Y plus 6 equal to 2x, or y plus 6 over 2 equal to x. So that would mean that I would use y plus 6 all divided by 2. Right? That's giving me the length relative from the axis all the way to this outer edge on the line, but that number is too large. I need to subtract the 2 units. That has nothing to do with little r, because little r starts from the axis of rotation and goes to the outer edge. So I would subtract my 2 units. Putting that all together, volume equals pi. Right? I'm working in dy. So let's see, my region starts at y equals 0 and stops at y equals 4. My capital R, square root of y plus 1, quantity squared. My little r, y plus 6 over 2 minus 2, quantity squared, and dy. So there's capital R squared minus little r squared. Put that all together, type it in your graphing calculator, you should be getting 16.755. Hopefully, if you had a solid foundation with some of the work we did yesterday with DISC, then you'll have an easier time with some of these harder ones where you're trying to move off of the 2 axes. DISC is easier than washer. DISC on the X or Y axis would be the easiest. A disc off the X or Y axis would be the next hardest. And then you'd move into washer on the axis. And finally, ones like this where you're moving your washer method and you're moving your axis of rotation off of the X or Y axis. That would be the absolute sort of hardest type of question to come across. But volume of solids of revolutions is super important. It is always heavily tested on your AP exam. So I wanted you to have a chance to see these notes and get some practice. The practice is actually listed at the bottom. I believe there's some links to some Khan videos. You also have some Delta Math you could try. But keep getting some practice. Both of these sections from 7.2 here, the previous video notes and this one are something we would come back to and practice. I am not expecting you to be an expert, but I did want to give you a chance to be introduced so that we can focus on practicing our skills in class when we do return. Thanks for watching. I think there's one more video for you to see, and then you'll have finished all of the Calc AB new content. So hopefully you're excited. It won't be much longer.